Well, all right. So it is the second week of January. So we are going to open up these, open up this link in a new tab here. Open up this link in a new tab. And this one, we're talking about exponential functions, which is interesting because we have been living, in exponential function reality with all this disease and stuff going around. That is the multiplication practice. The multiplication of it is exponential, and that's why people get so worried, right? I don't know why this is so small. Increase the size. Okay. So is this the first one? Exponential versus linear growth. All right, so exponential versus linear growth. So we already know that linear has a slope, right? So let's write that down. Slope, we know the slope is y2 minus y1 over x2 minus x1. That's for linear. All right. And this we call a constant difference. Difference is subtract, right? So when you have a constant difference, there's a constant rate of change, and that's called a slope. All right, so that's what we've been calling it. Now, that's for linear. Exponential also has a constant change, but it's not difference, it's division or multiplication, right? Okay, so exponential we'll write down as a constant, wait for it, ratio. All right, so when we divide the terms, let's say we have when we divide, so let's say we have A, B, C, D, and we do D over C. As long as there's a constant change here, a constant difference on the x side, there's going to be a constant ratio on the y side. Now, what I just did there with the letters, I think makes it super confusing. So instead, let's just use this example. Okay, so I'm going to go ahead. Now I'm going to write down the x's 7, 16, 25, 34. And I'm going to write down the y's 5, 10, 20, 40. So let's check for linear. Add 5, add 10. Okay, it already failed the linear test. Well, let's make sure we have. On this side, we're adding 9, adding 9. Okay, so it failed the linear test because the linear test would be 5 over 9 and then 10 over 9 are not equal. If it was a slope, it would be equal. So fail the linear test. But guess what? There's another test, exponential. So for exponential, the first thing we do is we check to make sure that we have a constant difference in the x's. So as you can see, we're adding 9 each time on the x side. So that is first step. It might be exponential. Now on the y side, what we do is we divide the terms. So instead of subtracting like y2 minus y1, we're dividing. 10 divided by 5, what's that? 2. 20 divided by 10, 2. 40 divided by 20, 2, we have a constant. Ooh, look, an example of a constant ratio. So this is exponential. Go ahead. Verify that. Oh yeah. All right, let's do one more. So now what about this one? So checking again for a constant difference in the x's. So from 22 to 18, that's we're adding 4, adding 4, adding 4. So that checks. Okay, now let's see about this. 12. Oh, we're adding 4. Are we adding 4 again? No, we're not adding 4 again. So it's not linear. It might be neither though. Now we have to see if there is a constant ratio. So don't jump right to exponential. You have to divide 12 by 8. And we also have to divide 24 by 2. Well, I don't even have to go into the actual division because I know that 12 over, oh, I'm sorry. 24 should go on top. I know that that's 2, and I know that this is not 2. It should be 16 for it to be 2. This is not equal to 2. So we do not have a constant ratio. No. So sad, so sad. So this one is going to be neither. All right, so there's a good starter for that one. Let's look at exponential versus linear models. So when we have a model, it's not going to be exactly a common difference or a common ratio, but it's going to be close, okay? And then the other thing about a model is the growth for a linear model is going to be a specific amount, and then the growth for exponential is going to be a specific percent or growth factor. Okay, let's write that down. Linear, constant, amount of change. You know, example, plus 100 people. If the town is growing by 100 people each year, that's linear growth. That's a certain amount of people. Exponential has a constant factor. So example, the town is times 2 people each year. You know, the town is, or, you know, 1.02% each year. That's another growth factor. So percentage is a big indicator that it's exponential, although there is a certain way we could word it so it's linear, but percentage growth in general is going to be exponential. So the number of visitors to the Eiffel Tower increases by 1.5%. That's a percent, that's exponential. Every year, 39 million cars. So that's not a factor, that's a certain amount, so that's linear. One more. So here, what you're going to do is you're going to find the linear, you're going to do the linear or exponential analysis, just like we did in the first assignment, but it might not be exactly, but it will be close. It will be closer to linear or closer to exponential. So in this one, find if there is a slope. You know, if when you choose 2 of the points, if you get like 2.1 and then the other time you get 2.01 or 1.98, then we could say like, okay, that's approximately a slope of 2. So we would say linear. But also check exponential. If you divide the terms and you get growth quotient that's approximately a certain number, then it's exponential. Okay, so I'll let you go through that and try it. Let's move on to the next one. Word problem. So now that we've talked about all this, we've done most of the basics. So the rest of it shouldn't be too bad. So already we can see 6%. Oh, there's one more basic. The basic equation. So exponential expressions have basic equations just like linear ones do. We know that linear is y equals mx plus b, right? Okay, well, exponential is y equals a 1 plus r to the t, something like that. Okay, and this is our y-intercept, our initial amount. Inside parentheses, the 1 is always there, and then the r right there is our growth percent, and you write it as a decimal. So if there's 2%, you would write 0.02. And then I should also tell you that the whole inside, when you add the 1 to the percent and you put the number together, that would be the growth factor. So if you had 2% growth, then 1.02 would be your growth factor. Just simply adding 1 to the number. And then if you have a decay, a percentage decrease, you just subtract 1 from that number. All right, and then the last thing to say is that T stands for time usually, and that's going to be our independent variable. Okay, so in this one, we have $80, 6% additional manpower, 3 years. So that's going to look like this. 80 is our y-intercept. 1 plus 0.006 for the 6%. And then the time is 3 years. So there's going to be an exponent of 3. So again, following that equation right here, we put the y-intercept in for A, the number in front of parentheses. We put our growth factor in for R. It's going to be given as a percent. You need to move that decimal over 2 spaces, make it into a decimal, and then the time goes in for your exponent. All right, so when I look at the choices here, I don't exactly see this, but I do know exponents means multiply the same thing 3 times. So that would be this right here, right? Let's try it out. All right, let's try one more here. Shada invest $1,000. So that's going to be my A. Here, see, they didn't give us a percent. They gave us a factor this time. And the value after 5 years. So it's going to be 1,000, 1.02 to the 5. Pretty simple. And so when you're trying to do this multiple choice, just stay away from the plus signs there. All right. Should be good to get you started. Now let's look at interpret the exponential expression word problems. The expression 4 times 3 to the t gives the number of ducks living in Anoop's pond T years after he built it. What does the 4 represent in this expression? All right, so remember that I told you A1 plus R to the T, and this whole thing is the growth factor, right? So here, 3 is the growth factor. So the ducks in this pond are actually tripling because there's a 3 as the growth factor. That means triple. 3, 9, 27, 81, and so on. 4 is the initial value. So that 4 being there means that there was originally 4 ducks living in the pond. Let's see if I'm right. Verification. Oh yeah. All right, last one. Okay. So 5 questions. Functions. Remember that the functions, okay, so there's some different questions here, about functions. Remember, this is interleaved practice and things we've done before. But recall that this means we got to substitute that 3 in. 39 minus 2 is 37. Hopefully you don't get the exact same questions I'm getting. Okay. Remember this one. We want to take that. We want to find f of 0. F is the blue graph here. And so at 0, it's at 1, it looks like. And g of -8, g is the pink graph here. -8. Looks like it's -7. So -8 times 1 plus 4 times -7 is -8 plus -28, -36. Uh-oh. Now you know. -32, 24. Okay, so I get the -8 right, but it looks like it was -6, and I thought it was at -7. So not too bad. Oh, okay. Aha, now remember this one. So for this one, we want to take that 4 and set it equal to the expression, and then solve it. -16 equals 4t. Divide both sides by 4. T equals -4. And what is the input value when f of x equals -3? So now we want to know the input. They gave us the output, and they're asking us for the inputs. The output axis is the y-axis. So we're going to draw a vertical line. A horizontal line across at the output of -3. And we see that it hits the function right at here, which has an input value of 5. So when x is 5, the function has an output of -3. And the last one. Okay, this one is very similar to one we already did. So hey, give those function assignments a try and those exponential function assignments a try. And I will see you online in class one more week. Bye, everybody.